Hello and welcome to lecture 6. So before we get started with the rest of the lecture slides from last time, I have a few things that I wrote down that I want to talk about that are more random things, but you'll need them on future labs. So the first thing is called preprocessor directives, which is a fancy term. I'm going to give an example with just like a hello world kind of piece of code. So let me take this hello.cpp from last time, and let's make a new C++ file that does very simple things, but let's make a short, tiny hello world library, maybe. Let's make a function that prints out hello world, maybe. Void print hello, and then we'll just do that. And then let's also make a declaration for this, because then we can put it in a header file. Okay, and then the main function will just call this, and that'll be that. So the idea is, I guess this is like the use hello file. Use hello.cpp, and then we'll make hello.cpp and then a hello.h, and that should do it. So we'll take all that stuff, put it right here, put that right there, and then inside of hello.cpp we're going to include the header file, because that is customary and it helps a lot of the time. And in the header file, we can also do the thing like include iostream and use namespace std, because the header file is going to get copied and pasted into anything that includes it, and print hello needs to use cout, and that is defined in iostream, and it needs to also be qualified with that std : so by including it here, we now have it at our disposal. And then here, if we want to use the print hello function, we have to include hello.h. And I think you now remember how to compile all these things. We're going to do g++, use hello.cpp into, let's actually do it the long way. Let's make use hello.o. Let's do the same thing for hello.cpp. I'll make hello.o. I'll do the same thing. That's all the CPP files we have, so that's perfect. Then we can link these things into our final executable, g++-o use hello. And then we'll bring in all of these compiled files. So use hello.o and just hello.o. This, I should probably not be saying make, because we know what that means now. Create. And this will create final executable. And we're going to call it use hello. Okay, so those are all the things that we're going to do here. I think I don't have a terminal yet, so let me work on that. Let's make it small, and then zoom in. There we go. So cd desktop, CS16, spring 2020, code from class, and lecture 6. Okay, so here we are. Let's do all these things. g++-c use hello.cpp, and this is going to create for us use hello.o. Now we're going to do this one. No, what have I done wrong? Oh, I didn't spell include correctly. Sorry about that. Which one's that? No, it's right here, right in front of me. There we go. And then we'll bring them all together and compile the final thing. And this is nothing new. So I just got to this point to show you something else. It's also customary in your header files to include the following in your at the start and end of your header files. So it's if and def. This is a hash sign, meaning this is not C++. It's like the preprocessor thing, just like include. starts with a number sign. If not defined, and then you usually give the name of the header file. hello_h. You can't use dots because this has to be an identifier. Then define hello_h, and then end if. And this is at the start. Start a file, and this is at the end of file. So you wrap this all up in these things. So if not defined, please define it, and end if. This is like an if statement at the level of the C++ preprocessor that looks at your code before anything else happens. So all this is saying is, I'm going to make a fancy variable. This pound if and def stuff makes sure that hello.h is only ever included once in your files. And the reason that this is useful and important is because it's possible to get into infinite loops of inclusion. And this stops that from happening. So there's normal ways to get into this infinite loop of inclusion kind of stuff where you have like, I don't know, x.h and y.h, and x includes y, and y includes x. So this would then copy all of this right here, and then it's going to see this, and oh, I need to copy all of y again into itself. And this will go back and forth, copying each other for forever and ever until the end of time. Let me set that up for you to see. I'll just use hello.h. I think I can make it work. So let's turn these into comments. And inside of hello.h, never do this, I'm going to include hello.h. Never do this. Uh-oh. Uh-oh. So it's going to see this, and oh, all right, I need to copy and paste hello.h right here. So it does it. And then again, it sees this include, because it'll be a second time at that point. It's essentially doing this there, and then replace this with that, and oh, here it is again, replace this with that. And it just makes a million lines of garbage. That's the idea, this kind of infinite inclusion. We don't like that. So let me show you it happening. And here is the giant error that you get. It's like, include, in file included from itself. So include nested too deeply. This all means lots of issues. So you got to scroll up to even see the problem. In file included from. If you ever see this, that means you've gotten yourself into a chain of nested inclusion. And the solution is to cut it off, because what this is doing is it's defining a special variable called hello_h in all caps. It's just customary to use all caps. And it's saying if this special variable, special compiler variable, doesn't exist, only then include the contents of hello.h. So you put this at the start, at the very start of anything you ever do. Because at that point, any other inclusions that live inside of this will only ever get included once, as long as they're also following this pattern. So this makes sure that if we include hello.h, and even if it includes itself now, what's going to happen is this. The compiler is going to be like, all right, I haven't seen this before. I'm going to define it and include the rest of this file. And oh, it's asking me to include hello.h. Sure, I'll copy and paste it. But it's going to get right here at this new if statement and see that, oh, I already defined hello.h up here. I'm not going to follow the body of this if statement. So it's essentially commenting out all of that code and not including it. And so at that point, you've stopped that kind of infinite loop of inclusion. And that's beautiful. That's exactly what we wanted. So here, even with this issue, I can include this in itself. And it's going to stop early because this hello.h, this special compiler variable, is already defined. So, oops, I clicked on the wrong thing. Let me now do it again. And it works just fine, even with this infinite inclusion. But this is okay now. because we wrapped this entire file in a compiler level if statement. So that's what that is. Whenever you make a .h file, please do this. Just take the name of it, replace it all with all caps, and replace the dots with underscores. And for some reason, people also like to put an underscore at the end. And just do this in this pattern. If not defined, define, end if. Put your entire file in that, and it stops this kind of infinite inclusion. Okay? That is all for that. So use that, if and def. All right, next example. I want to talk about global variables versus local variables. And you might have read about this in your book, but I want to just give an idea of them. Global variables versus local variables. So the idea is global variables live forever, local variables have a certain lifetime. Live for the entirety of the program, while locals live for the block/function, live only for the block/function that they're defined in. And a block is something in between parentheses, like your for loops. If you say for int x equals 0, blah, 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 the x variable goes away after the loop. X is gone here. Okay, that's the idea. And let me give you an example. A nice colorful example that I like to do is using Harry Potter, and I think you guys might be, this might be a bad example these days because less and less people were addicted to Harry Potter. That is me showing my age at this point. So let me make, I don't know, a global variable with, I don't know, it'll be called Harry Potter, okay? And, I don't know, his value will be 7. And this is declared outside everything. That's how you make a global variable. It lives outside any possible function. And then let me make a function whose name is one of the books from Harry Potter. It's called Goblet of Fire. And if you remember this book or you watch the movie, let me change Harry Potter because I can access any global variable. I don't know, plus plus. And then let me make a local variable. And I will aptly name it one of the characters from this book who unfortunately dies in it. So I'll make a variable called Cedric. That is his name. This is the person who died in the book. And let's give him 10. And the idea is global versus local.cpp. Local variables, they go away after functions. Locals go away after functions return. They live for the life of a function or a certain block that they're defined in. Okay, so I'll call the Goblet of Fire function. And I can do things like, I can print out Harry Potter before and after. And then I can do the same thing here. And I can print Cedric in its own function where it's defined. But the issue is Cedric doesn't exist out here in main. I'll actually get a compiler error. And I'm going to compile this in a special way. I'm going to use those default makefiles that we all know and love now. So I'm going to say, instead of g++ -o blah 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 blah.cpp, I can just say, as a shorthand for that, make global versus local. Use the default make rule to compile this program. And down here it's saying Cedric doesn't exist in main. Okay, sorry about that, Cedric. And now when I run the program, it'll totally work. I can access any global variable anywhere in the program. So down here, I'll print out Cedric because he's a local variable and he lives in this function only. And then Harry Potter got changed because he's a global variable and I can access him anywhere to one more than what he was before. So the idea is local variables, sorry Cedric, local variables die and global variables live forever. So for example, if I were to draw the stack diagram, like we did in a previous lecture, the main function has a certain number of variables, and I have not defined any special variables in main. I didn't even give any command line arguments, so main has no local variables. And Goblet of Fire has a local variable called Cedric. And the idea is once this function returns, Cedric goes away. All of that memory gets reclaimed. All local variables get reclaimed in memory after their containing function / block ends. Okay, but Harry Potter, this is like this is the function call stack, right? So this is the stack. Yeah, come on. No, I want to draw. This is the stack. There's a separate space in memory for your global variables. Global memory space. And it lives somewhere over here, separate from the stack. And that's where Harry is right now, for the life of the entire program. All right, so he started out being 7, then he became 8, and he doesn't go away until the entire program ends. Okay, global variables live for the life of the program, while local variables sadly go away when their functions return. And let me just make this red. Okay, the boy who lived. That is the idea. Okay, so that's globals versus locals. And one last thing before we go back to our slides is something called break versus continue, or break and continue. They are parts of loops. So can I use my hello.cpp? So all I need to do now is make a, no, first of all, I don't need to include anything for that file. Second of all, let me make some loops. So here is a loop for int I equals 0, I is less than 10, I plus plus, or let's count from 1 to 10, not 0 to 9, and I'll see out I. So it'll count from 1 to 10, new line. Then I'll do the same thing down here. So I'm going to count from 1 to 10 twice. And let's actually use a while loop this time, just for fun. So same thing. All right, so this is just going to print out 1 to 10 twice right now. And there it has done it. So I just want to talk about this. You might have learned about this before in a previous class, but there are some keywords that you can use inside of loops. There are 2 loop-specific keywords that you might need to use one day. And we'll actually be using it later in this lecture if we have time. The first is break, and the second one is continue. I would like a lowercase b, please. There we go. And continue is the other one. So break stops the loop and continues the program past the loop. Starts executing the lines after the loop. And the program starts executing on the lines past the loop. And continue is doesn't stop the loop, it stops the current iteration of the loop. And what it's going to do is then tries to perform the next iteration. So let me put these in bold and let me give you some examples of them. So you can use it in any kind of loop, for loop or while loop. So let's say we hate the number 9 and we want to stop the loop whenever we get there. So if, and we don't even want to print it out, so I'll do it up here. So if I happens to be 9, psych, we don't want to go until 10. We don't even want to go until 9. Let's stop the loop here. Stop the loop before printing 9. Okay? So now this entire loop will print 1 through 8 only, because we're going to break out of it whenever we see the 9 before we print the 9. Okay, so now it's going to print 1 through 8. And you see it there? Maybe I can make this slightly taller. It's hard to find the little place to drag. All right, and then the other one's still the same. Now this one, let's say we hate the number 9 still. We don't want to print it out, but we don't want to stop the loop. We want to continue to 10 as well. So if I is equal to 9, let's continue. Don't print out 9, but continue with the loop. Don't stop it. That is so we can still print out 10 and things after it if there were more. So now, if I were to run this, it's going to, oh shoot, what have I done wrong? Yes, so now I had an infinite loop, sorry. So before I continue, I should also increment I so that it'll change eventually. I++ continue, sorry about that. And so now, whenever it's 9, we stop the loop, or we stop that current iteration of the loop body so that it goes to the next part of the loop. And make sure, if you're in a while loop, that is, to increment your variable that you're checking, if you're doing it that way. So it doesn't stop the loop, it just brings it right back. That's kind of like, we were here in the body, and here's the condition. Continue makes it go right back to the, check the condition, and do the body again. That's the idea. It immediately jumps up to that condition, trying to do the loop one more time, if it can. Multiple more times, that is. So that is break and continue. And now I think we are ready for our regularly scheduled programming. So back to number conversion. Let's talk about a new kind of system called hexadecimal. So we've talked about converting between binary and decimal both ways. That algorithm works for any base, by the way. Let's talk about base 16. This is useful for programmers for a number of reasons. So base 16, hexadecimal. Base 16 is called hexadecimal, hex for short. And you know, like hexagon, that's 6, and then decimal is 10. Add them together, you get 16, right? So that's the idea. Hexadecimal. The digits are 0 through 9, of course. But that's only 10 digits. We need 5 more, because we need to go from 0 to 15, right? So let's make new digits up. A, B, C, D, E, F as well. Okay? Those will be our digits. And so we can have numbers that look like 1A, F, F. These are hexadecimal numbers. Okay? So, here are their corresponding decimal values. So 0 is 0, 15 is F, and it just so happens that programmers love hexadecimal because they correspond, a single hexadecimal digit corresponds exactly to 4 binary digits, okay? A hex digit corresponds to 4 binary digits, padded with zeros at the front, if necessary. Okay, and I'll show you why that's cool in just a second. It's because the base is also, base is 16, it's a power of 2. That's pretty powerful for us. So for example, the number 3 in binary is 1, 1. If you pad it with enough zeros to make it 4 digits long, it's 0, 0, 1, 1, and that will represent the 3 in hex as well. Then F is all of those things being 1, 15. All right, so let's do 25B, base 16. Let's first, actually, before we go to binary, let's convert it to decimal, just for fun. Or is that on the next slide? It is. Okay, so let's go to binary first. And this is the magic of hexadecimal. 25B in base 16 equals what, base 2? Well, remember that each digit corresponds to 4 binary digits, padded with enough zeros if you can do it. And that's the idea. So let's replace the 2 with 4 bits that make 2. So 0, 0, 0, 1. We can actually get rid of these. Oh, sorry, that's 1, 0. That one. We can actually get rid of the leading zeros for the first digit. So these don't actually have to be there, but the others do. So then we can make 5, which is 0, 1, 0, 1. Then we can make B, which I don't remember. It's 1, 0, 1, 1. And if you put these all right next to each other, that is the answer. That is exactly the answer. 25B base 16 is, getting rid of these leading zeros, it is 1, 0, 0, 1, 0, 1, 1, 0, 1, 1 in base 2. Okay? And the reason you can do that, split it into these groups of 4 bits, each digit. The reason you can do that is because the bases are powers of each other. Okay? So let's remember to split this up. 25B. That is 2 times 16 squared plus 5 times 16 to the 1 plus B times 16 to the 0. And remember that the B in decimal represents 11. Sorry. So the reason you can just start putting these digits next to each other and not actually have to do any kind of calculation is because this base is a power. 16 is a power of 2. And so let's then convert this to binary. So this is 0, 0, 1, 0 times 16 squared again plus 5 times, plus 0, 1, 0, 1 times 16 plus B, because it's just times 1, right? So the B stays where it is. That's 1, 0, 1, 1. And let's add to that. So let us start with this one. What is 0, 0, 1, 0 in binary? 2 times 16 squared. So let's talk about how to multiply something by 2. To multiply a number in a base by that base, you add a 0, which is super powerful, because if we're in decimal and we say, I don't know, 10 times 10, well, that's 100, right? Because we're multiplying by the base. Same thing's true in binary. If I have a binary number, 1, 0, times 2 base 10, well, which is really 10, 1, 0 base 2, these correspond, right? That equals this with another 0 added to it. 1, 0, 0, because it's 2 times 2 is 4. 1, 2, this is the 4's place. And that is the answer. So this, because it's a bunch of 2's, because 16 squared equals 2 to the 4 squared, right? This is equals 2 to the 8. This plus 8 zeros, which is essentially this shifted all the way over, okay? So let me try and make this logical. So it's 0, 0, 1, 0 with 8 more zeros. 1, 2, 3, 4, 5, 6, 7, 8. You see how that made room for those other 2 digits? That's exactly where I'm going with this. So it's that plus, so that's this one. Boop. That's this one. And then now let's do this one. 0, 1, 0, 1 times 16, which is 2 to the 4, which is 0, 1, 0, 1. Let me get these all to correspond with each other. 0, 1, 0, 1 times 2 to the 4, so add 4 zeros. Yeah? See, and you see how that left room for the other digit. This is all base 2. So that was this green one, this green number. Plus B, which is 1, 0, 1, 1. plus 1, 0, 1, 1. There's no carrying involved. I'll talk to you about how to add binary numbers later. That's this one. The B lives right here. There's no carrying involved, and you just start adding them all up. So you just take the first one, 0, 0, 1, 0, and the second one, 0, 1, 0, 1. You see how this all works. And then the 1, 0, 1, 1, base 2. And that is the answer. You can also get rid of these leading zeros. Okay? So that is the reason you can go immediately, you can read off from a hexadecimal number its binary equivalent by just converting each digit into 4 binary digits, because 16 is 2 to the 4. That's the idea. You can shift, you can add a bunch of zeros. You can just start reading that off. Okay? That's the answer for that. So that's 25b, base 16. This is what it is in binary. Okay? And let me just write like an X or something there instead of that. Much better. Okay. Now let's convert this to decimal. So 25b, base 16. It's 2 times 16 squared plus 5 times 16 plus b, which is 11 times 1, because that's 16 to the 0, right? And so 2 times 16 squared, let's just do this in Python. 2 times 16 squared plus 5 times 16 plus 11 happens to be 603. Okay, so you can see how smaller looking things, because the base is larger, become large numbers. Okay, and it's easy to always convert from a base that is a power of 2 into binary. All right. Yes, so that is exactly what we did here. Decimal to hex, now we can do that same idea from last time. If I go to the lecture notes from last time, this process of repeated modulo and integer division. If you remember that process from last lecture. We'll do that all over again, just with a new base. All right. So let's start at 36 decimal, and then go to base 16. Okay. Let's start at 36, and in order to go to hex, we're going to repeatedly mod out by the base that we want, which is 16, and also integer divide by it as well. So 36 mod 16, I think it's 4, because 16 times 2 is 32, and 4 more make 36. And then 36 integer divide by 16 is 2, okay? Because it goes in 2, not 3 times. It's 2 point something, and all those decimals go away. And then we work with the 2 now, and try and shift that out and get its digit, its next hexadecimal digit. 2 mod 16 is 2, and then 2 integer divide by 16 is some decimal that's less than 1, so it becomes 0. And that's how we know we are done, and every time we took a modulo operation, we get to read off a digit in reverse order, remember. So 36 base 10 is 24. I shouldn't be saying 24 because it's not base 16. And we can always check ourselves by converting this back to decimal, which is 2 times 16 plus 4. So that's 32 plus 4 equals 36. Okay? So that is that idea. Now take a second to convert from binary to hex. And assuming you've unpaused the video now, one thing that you can do is go from binary to decimal, and then use our algorithm to go from decimal to hex. That would work. But you can also do that other thing in the reverse order by grouping these into groups of 4 bits. So what's 1100? Well, it's C. What is 0011? It's 3. And what is 10? It's 2. And we can just immediately read it off like that. And you should check yourself to confirm that that's true, that trick works. So it's 0b, all of that, 572, and 23c. 0x will convert that from hexadecimal to decimal again. These are both 572. They're the same decimal number. So the answer there is B. Oops, I did not want to make you smaller. So this is now B. And let's see here. Yeah, I think that's where I wanted to go with that. Briefly, let's talk about another base. One more useful base is base 8, which is called octal. You can do the same trick to convert between octal and binary like you did for hex and binary. Remember that 8 is 2 to the 3, so each octal digit is represented by 3 bits, okay? So if I give you an octal number, like 4, because the digits can go between 0 and 7, you have 8 of them. If I gave you an octal number like 451, to convert this into binary, you'd again take each individual digit and convert that. So 4 is 0, or 4 is 101. It's 3 binary digits. Remember that. So the 4 is 101. The 5 is, oh, I'm so sorry. That was 5. The 4 is 100. The 5 is 101. And the 1 is 001. Okay? And this is now in base 2. It's an easy way to convert in between octal and binary. Okay, moving on. Why do we care about any of this? Well, we're using computers where everything is in binary. And so you should understand that we're representing with bits, some amount of them, everything that we could ever talk about. Like this video that's being sent to your screen right now, it's just a bunch of bits, just a really long number, right? So we can represent anything. We can represent numbers for sure. So we can represent 0, 1, 2, and 3 in some binary coding system. And now my question for you is, how many bits are required to represent the numbers 0 to 3? Just 0 to 3, the minimum amount of things. So take a nice guess at that. Well, the answer is 2 bits, because we can have 0 be represented by 0, 0, and 1 represented by 0, 1. Or let's try just 1 bit. We can have 0 be 0, 1 be 1, but then when we need to get to 2, we don't have room for it, right? We can't do it 0 again, we can't do it 1 again, so we have to add an extra place. 0, 0, 0, 1, 1, 0. And then 3 can be 1, 1, okay? So we needed 2 bits to represent these 4 numbers, okay? And again, we can represent anything. We can represent, like, complex things, like how many, we can represent red with a certain binary code, green with a binary code, blue with a binary code. And if I zoom into this, what's the minimum amount of bits that you need to represent these 3 colors? Not 4 anymore, but 3. Well, green, blue. The idea is, okay, we can't do just 1 because when we get to blue, we have no space. So we have to use 2 bits. That's the minimum amount. We can encode it like this, or some other combination of different numbers. But we wasted like 1, 1. We didn't have any need to use 1, 1, and that would have filled up all of our possibilities. But we can't have like fractions of bits, so we had to go to 2 bits in order to represent that third thing, okay? So you still needed 2 bits even if you only have 3 things now. And now we have characters as well. Characters are just a certain, in a certain encoding, they're just a bunch of numbers. So A, when we print it out to the screen, we're really sending a certain number that represents the A character to the screen. And so what I want you to get out of all of this stuff is that n bits can represent 2 to the n things, because 0 and 1, there are 2 to the 1 things, right? 2 to the 2 makes 0, 0, 0, 1, 1, 0, 1, 1. that's 2 bits, make 4 different things. And then 2 to the 3, if I want to do it out for you, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 8 things, okay? N bits can represent at most 2 to the n things. So now, think about it. What is the minimum number of bits that you need to represent all the letters in the English alphabet in lowercase? So there are 26 letters of the alphabet. So let us now go to and look at that. So we need to represent 26 things with a certain number of bits. So let's try 3. That will give us 2 to the 3 things. 3 bits would represent at most 8 things. That's not enough. 2 to the 4 would represent 16 things. Not enough. 2 to the 5 would represent 32 things. That is enough. That's the minimum amount of bits required to represent the English lowercase alphabet. We need at least 5 bits. So we did waste some space. We're saving 26 things, but not 32. So we're going to have some numbers that we're not using, but 2 to the 5 was necessary. Okay? So that is that. And yeah, so the idea is bits can represent anything. All of these logical values, false and true, colors, characters. Remember, it's not 2 to the 26. It's not 26 bits because 26 bits can store this many things. It's a lot. You don't need that many. So memorize this fact. It might come up on a test. And then for many different languages, we use this encoding called Unicode, which has very long strings of bits that can represent many different, like all the alphabets of the world, any character set. And then, of course, we're already using them to represent like addresses in memory. All of our programs even are just really long numbers. So now, let's go back to some terminology. What's the maximum positive value that you can store in a byte? And remember that a byte is 8 bits. All right? So you might be thinking that, okay, a byte, 8 bits, 2 to the 8, that's 256, isn't it? Yeah. So the answer is D, right? No, it's not. It's 1 less than that because, remember, 2 to the 3, for example, the minimum number was 0, and the maximum number was all 1s, which was 7, which is 2 to the 3 minus 1. So really, we can represent 8 digits of binary, so from 0 to all 1s, which happens to be 255. Okay? So don't trick yourself with that. Don't get tripped up there. It's always 1 less because you're going to go from 0. You're starting from 0 always. You're storing 256 things total, but it doesn't end with the number 256. Okay? That would take an extra bit. And then there are some data types that we can use here to talk about things like 8 bits we already know is a byte. There are some other things that you might see one day. 16 bits is known as a half word because 32 bits is a very common thing. It is a word. Integers are actually stored in 32 bits, so we say that integers take up a word of memory. And then 64 bits is relatively new. We all have these 64-bit processors nowadays. Those are like 20 years old, being popular. These are also called double words or quad words. So yeah, it all depends on what data type you're using. So the data type of a variable determines what it's going to look like in memory. So like if you're using characters, there's a certain number that represents the character A. And it's also going to determine the number of bits that you're going to use because like an int, for example, is going to take up 32 bits, and a character is going to take up only 8 if it's just like an English alphabet character. We use the ASCII encoding that you're going to remember from a lab, and that only takes 8 bits to store all of those characters. Actually, if I can go to your textbook, I'll show you that very quickly. Dun dun dun. Table of contents, appendices. This will come up later. But here's the ASCII character set. we only need to store this many things. We actually use 8 bytes. So the lowercase character a is represented by the number 97. So food for thought. And yeah, the range of values that can be correctly represented also is very important. Because, for example, we're only going to be able to store 32 bits of things in an integer. So there's going to be a maximum integer that you could store and a minimum one. Okay, so think about that. And with that, we're at the end of these slides, which are the slides from last time. So I said like lecture 5 and 6 for this title. And then let us now go to the code, because I want to make a program now that converts between bases, converts a decimal number to a certain base. Let's make a program to convert a decimal number to a given base. Let's say between 2 and 16, because we know those. So between binary and hex, let's figure this out. All right. So let's go into Visual Studio Code, make a new file called convert2base.cpp, and let me get all of this boilerplate up in here. Now, a main function. I'm going to be lazy and just write the function up here. So we're going to make a, let's have it return a string. So string convert to base, int decimal number, and int base to convert to. All right. So we're going to get two things from the user, int n and b. So C out, enter a number, cin n, and then we're also going to enter in a base, cnb. And then we're going to print out n in base b is, and then we're going to convert to base nb, and then new line. All right, so that's the idea. So let's make this convert to base function. And remember, we're going to code up this idea of multiple times doing this kind of modulo by the base and divide by the base integer divide. So we're going to start with our decimal number. So while it's not 0, while decimal number, that was our stopping condition, right? While it's not 0, mod by the base to get the next digit, and then integer divide to get the shifted number to find the next digit in, right? So the idea is we never want to be given a number that is 0, because if it's 0, this actually won't work very well, because that'll be our stopping condition. So if our number happens to be 0, decimal number, and this function, I'm going to not make it work for negative numbers right now. That's too complicated. It just won't work properly. So if decimal number is 0, then we're going to return the string 0, because 0 in any base is just 0. So otherwise, if it's not 0, let's forget about the negative case. Or we can just say, like, I don't know how to do it. If decimal number less than 0, return question mark. Like, this doesn't work for negatives, this algorithm. And if you haven't heard the word algorithm before, it's just a set of steps. It's like a recipe. So we're writing an algorithm right now to convert a certain number to a base, and an algorithm is just a sequence of steps, which is, in our case, lines of code. So let's now get back to the normal business. Let's mod out by the base to get our next digit. So next digit equals decimal number mod base. Okay, so that's our next digit. And we want to build up our result. So string result equals that. And remember, we're always getting the rightmost digit. So we're always going to be adding to the left of our string. So result plus equals So this is where we need to do some interesting stuff. So right now we have a digit. It's an int. We need to make it a string somehow. We can't just say plus equals, I don't know, next digit, because that's not correct. So I'm going to talk about this in a little bit, what we're going to do here. Then we're going to integer divide to get the next digit. So decimal number is whatever it was divided by the base. And we're just going to keep continuing while it's not 0 and getting the next digit to return. And then once we're done, we're going to return a result. Okay, so the idea now is to convert a certain digit to a character, to a single character. If it is 0 through 9, like it is here, string 0 should map to the character 0. And 9 should map to the character 9. But things like A, if we want 11, we're supposed to be in hex at this point, it should be A, right? So we need a way of converting integers to characters. So 0 needs to go to the character 0, and the character 0 is in fact not at all the number 0. So if I go back to this ASCII table, the character for 0 happens to be ASCII, the integer number 48. That's just what people decided. So we have to do something else here. And here is the solution. We can actually add characters. Or we can actually index into strings. So I'm going to make a string digits. And I'm going to do this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And this is kind of like cheating. This is useful because digits I equals the character I want. So I can index into digits. It's like a list in Python. It's like an array, if you've heard of that. So digits 0, the first character in digits, is the character for 0. And the 15th thing is the character for F. So I can say result plus equals, or actually result equals digits, next digit. So whatever it was, if it was 11, we're going to make A, or if it was 0, we're going to make the character 0, plus whatever it was. Okay? And this, if you stare at it long enough, this should be somewhat close to correct. So let's check ourselves. Let us convert now. Make convert to base using that default make rule. Let's convert, I don't know, 16, or no, 15 to binary. Yeah, it's a lot of ones. That's good. And I forgot a space here, it looks like. Let's do it 15 in hexadecimal. That's F, yes. 255 in hexadecimal is also is FF. And let's see here. What's another one that we know? Let's convert 5 to binary. 101. And this works for any base in between as well. So apparently 123 converted to base 7, or base 8 octal, is 173. And we can check ourselves by converting that back to binary. So 1 times 8 squared plus 7 times 8 plus 3. Yeah, that was 123. So that is my base conversion program, and I hope it makes a little bit of sense to you. And I think that is essentially what I wanted to talk about. Oh, one extra thing. Let's say if we don't provide a certain value for a number, for an argument, we can do these things called default arguments, and I don't know the best place to give an example of that. Let me just make a brand new program. That's something that I forgot to talk about. F, let's say here. So int f. Let's have f return its parameter x plus 1. Okay, so let's write our function f. Cout f of 0, because that'll return 1. cout f of 1, because that'll return 2. And then cout like f of 3, because that'll return 4. This is default arguments.cpp. This is a new thing. Default args. So in C++, sometimes you want to call a function with an argument that you already know about. In C++, you can give a default value for an argument in your function definition. That value will be used if you do not supply an argument for that particular parameter. All right? So, for example, x, right now it doesn't have any default arguments. Let me compile and run this right now. Make default arguments. 1, 2, 4. Let's say that we usually are going to call this function with 3. Like, I don't want to keep typing the word 3, so let's get rid of that. Let's use a default argument saying if I don't provide a value for x, like I'm doing here, I'm forgetting the value, the first parameter. And you can do this for any parameter, as long as it's one of the last ones. If I don't provide a value for x, use the default one for me, please. Otherwise, if I do, use that one instead. So this should print 1, 2, and then 4 3 times, because it's using the default argument in that case. Okay, that is default arguments. And now I think we are good with this entire lecture. And now, in the final few minutes, we have about 20 minutes left of this lecture, I want to move away from this topic to talk about a different one. So I want to go to Safari, just briefly, to talk about the midterm. If you look at all these things, all this stuff, this was the last thing that we're going to talk about. So right now, this new lecture is about files and reading and writing to those and from those. Files will not be on your first midterm, so we're going to cut off all the topics. So like from here. Number conversion will be on the midterm, but files will not be. Files onward. No, I don't want. Let's just say files won't be on the midterm for now. I'm pretty sure that anything else that I'm going to talk about is not also going to be on the midterm. I don't want to eat my words. So files are not going to be on the midterm, and I'm pretty sure that everything after this as well is not on the midterm. So you can stop studying right at this line in all the lecture notes. Okay? That is all. So now let's talk about files in the last few minutes that we have left. So we know how to do things in our programs. We know how to do inputs and outputs. To get inputs, we can read data in a few different ways. We can get it through cin. We know how to use our command line arguments now. We've got to define main like this. There's a third option. That one is called reading from a file. So we can write files on our hard drive or our flash drive or wherever we want to put it, and we can read from those things. And we can output things in different ways as well. We can output it to cout. Cair is a different place. We can also write to a brand new file. Okay? And so the idea is, when we want to read from a file, we'll do a certain kind of loop, and oops, I moved these around in a very weird way. I'm sorry. Let me change the order. I want to I think I first want to write from files. That was my first example. Let me confirm that. Files 1. Yeah, it was writing to files. Okay, so let's, I think, move this to right here. And I think that's everything I wanted to do. Okay, so first we have this fake iClicker question. Where are files stored? And I think I accidentally said it, but where do you think? The answer happens to be on some kind of storage medium, some kind of secondary storage medium like a hard drive. So the files are going to be stored on your hard drive. they're going to be read into memory when you want to access them and do stuff with them. You don't have to read the entire file into memory, but you need to read what you're going to work on in your current program into memory. And of course, if you're going to edit the file and do some stuff, you're going to eventually send some of the characters to the processor, because that's where the changes and all of the all of your algorithms that process your files are going to live. Okay? So with that, yeah. And then, of course, you're going to work on them. You're going to read the files in your programs, but this program is just something that's being run. Your files are actually stored in the memory, in the bytes, and the possibly the magnetic part of your spinning hard drive, or as like voltages in your flash drive, things like that. Okay, so that's that. Where are files stored? In secondary memory. Now let's talk about writing to files. And it's quite similar. We get to use these kinds of operations, just like we know and love from cin and cout, right? So a file that you can output to functions a lot like cout. Okay, let's go to fstream, because that is the new library for reading and writing from files. We're going to use ifstream and ofstreams. So in order to write to a file, we're going to include fstream, and then we're going to make an ofstream for output. Sorry, that was a typo. So we're going to open a file, and we can write to it just like we do in cout. So let me now go to my example. So here is files_1.cpp. So I'm going to include fstream, and that'll give me ofstream and ifstream. Right now I'm going to use ofstream because that will be for output, writing to a file. And so now we can open a certain file with a certain name. So what this is going to do, this line is going to act on our OFS, and it has a function defined on it called open. And we're going to give it a string that represents the name of the file in our current working directory that we want to create and edit. So if animals.txt didn't already exist, it would make it, and if it did exist, it would overwrite it. So be careful about that. So after this line, animals.txt will exist in your current working directory. And then you need to check whether or not anything went wrong. And you can reinterpret OFS, or a variable of type ofstream. We made a thing called OFS. You can call this anything, like my file, whatever you want. You can reinterpret that as a Boolean value. OFS interpreted as a Boolean represents whether or not anything went wrong, where wrong is up to definition. So let's just say if it couldn't open the file, that's something that is going wrong. So OFS would be false in that case, and not OFS would return true, and we should exit in that case because something went wrong with opening this file. It was false. Otherwise, we're going to write to this file by outputting it, setting those arrows because the data is going into the file, OFS. It's a file stream, we say. So we can write a certain amount of things, whatever you want, to this file. And then once you're done, you should remember to close it. Technically, it's going to get closed at the end once your program returns, once your main function ends, but it's good practice to close the file. And this dot notation might look a little weird. OFS dot open a.txt. This might look odd to you. You also saw this with cin, like setting those, or cout, sorry, setting those parameters for like making it so that decimal numbers are printed out with a certain amount of precision, like set precision, things like that. This dot and an open means that this is saying that there is an open function defined on this syntax is called a method call. If you take CS24, this will make sense then. I just want to say it now so that it's slightly less confusing. It's a method is a special kind of function that is defined on a variable. So it's kind of like we here in this line, we are calling an open function that belongs to OFS. You can gloss over this. I just wanted to say this now to make you slightly less confused. You don't have to pay attention or remember anything I just said. This is called a method. So OFS has a open and close function on it. And you can write to it using this cout kind of syntax. And so if I were to compile and run this program now, I could say make files1. It's not going to output anything to the terminal, but it made this new file, you can see it here, called animals.txt, and it filled it in with exactly what we asked it to fill in. And if I run it again, it's just going to, if I change it and I run it again, remember it's going to overwrite. It's going to take it back to whatever it wanted it to be. Okay, so that's files1. If you don't want to overwrite, you can do what's called append. Okay, so let's go to files 1.5.cpp, where I do everything the same, except I open the file for appending. When you say ofs.open, we make a variable of type of string. You can call this your file, whatever you want it to be called. What is called ofs. When you open the file, whatever it's called in your current working directory, if you say ios::app, that means open the file for appending. Appending means adding to the end of an existing file. Okay? So what's going to happen here now is when we open animals.txt, 1.5, it's going to open animals.txt, and if something went wrong, we'll stop. But if everything went right, we'll write to the end of the file. This time, OFS will write to horse. Okay? We'll add that to the end of this file that we're going to open. Okay? Let me get some of these out of the way. All right, so here's my animals.txt file, and I need to double click on it so it stays open in my editor. Okay, so now if I compile and run this, 1.5, oh, sorry, I just did it. If I run it now, again, it's not going to do anything, but it's going to take this file and add one more thing to the end of it. It's not going to overwrite it anymore. So I can run it a million times, and it'll keep on adding one line, that extra thing, okay? So that appending makes it so that it just adds to the end. And it'll also, it should make the file, if it doesn't exist already, it'll just put that as the first line in this case. So it's essentially, think about it like this. Appending is like you're in Microsoft Word, like your program opens up your file that you're writing to in Microsoft Word, and it puts its cursor, instead of at the beginning, it puts it right at the end so that you can start typing right at the end of the file. So that's what appending's doing. Appending puts the cursor at the end of the file. Okay, so that's appending. We have about 5 minutes left, so let me talk about reading from files now. It's slightly more complicated. So when we read a file, again, we're going to open it. We're going to use if streams now for input. Again, we'll check for failure, and then we'll want to read from it. Eventually, we want to read until the end of the file, wherever that is, because when we open a file, we don't initially know how long it is. So in a loop, we can do things like read a single line or read a single character if you wanted. And then the idea is we want to use this new keyword. We want to use break to get out of our loop if we ever reach what's known as the end of the file. And at that point, we should close the file because we're done reading from it. Okay, so that is the game plan. And converting this to code, again, we're going to include fstream. And then down here in main, we'll do all this stuff. We're going to make an IF stream now, call it IFS. We're going to open the file we want to read from, which should already exist, and check for failure. And then in a loop, we can call this getLine function. And we should declare a string line variable because every time we call this getLine function, it's going to read a single line from the file, okay? And if we read past the end of the file, IFS changes, sorry, this is a typo, IFS changes to false, all right? So that is the idea here. And eventually, it'll be a falsy kind of thing, and we can stop reading from it. And we should close at that point. So I think this will be our last example for today. If I go to my files2 program, and let's say I want to read from a file, so I'm going to include fstream, and then I'm going to make my ifstream object, call it IFS, call it my file, whatever you want it to be. We'll open our file to read from it, and check for failure. Again, IFS will be false in that case. Then we want to, in an infinite loop, keep reading. We'll read a single line at a time using this getLine function. And the getLine function, it takes the current line we're in from IFS, and it plops it into the line variable. So this function, unlike others, it actually sets the line variable. This sets the line variable, which is different than what we know about before. It's defined in the string library, this getLine function, right there. And it takes your iStream, in this case it's an IF stream, and it takes a string that we want to write to, and it reads that in, and it stores it into the string that we passed along. So you can read up on that if you'd like. But yeah, this reads a single line at a time, and eventually it's going to hit the end of the file. And once it's the end of the file, IFS becomes falsy again. At this point, if we didn't end the program with an error, IFS is true right now. Now IFS is true, in some sense of true. Once we read past the end of the file, that's essentially an error again. So IFS becomes false, and we can break out of our loop. And if we didn't break out, that meant we actually read a new line, and we can output the line. So this is essentially reading the file. This loop reads a line at a time and prints it back out. So really, it prints out the entire file. One line at a time, that is. So this loop, what it's doing, if I were to run this program, it's going to open the animals.txt file, read from it, and print out the entire contents of it, okay? And it's going to do that one at a time because this getLine function is going to start with its cursor right here. And it's going to read a single line, which is going to put its cursor right here now. And that's going to, again, in a loop, we're going to read a new line, and it'll put its cursor right there. So getLine, or IF streams start, lowercase, start their cursor at the beginning of the file, and getting a line with the getLine function advances the cursor one line. So every time I call that getLine function, it's going to move that cursor one by one by one by one until we eventually try to read past the end of the file, and I'll represent the end of the file like this. So end of file. Once we read past the end of the file, our IFS variable becomes false. And at that point, we should stop our loop because we have no more left to read. Okay? And remember to close our file, and then we're done. So please take a look at all these programs we talked about today, and remember that files will not be on the midterm. and we'll pick it up from here next time.